Let's talk about floating point numbers and what is the system of them. I want to start that with an example on a piece of paper. Let's talk about this floating point number. It consists of 64 bits, 64 times either 0 or 1. If this number is stored on your computer and it represents a floating point number, which number is that? A floating point number consists of 3 parts. The first part is this very first bit. The second part consists of these 11 bits. The rest is 52 bits. This is the third part. The first bit is the sign bit. So it's -1 to the 1. That means if this is a 1, it's a negative number. If this is a 0, it is a positive number. The next 11 bits, this is the Mantissa. It represents this number. It's adjusted by 1023. So let's see what's happening here. And now this is a dual number. This is the 1 bit, the 2, 4, 8, 16, 32, 64, 128, 256, 512, and this is the 1024 bit. So it's 1 times 1024 plus 0 times 512 plus 0 times 256 and so on, plus 1 times 1. So this number, being a dual number, represents the number 1025. So these green bits, these are 1025. And now we get the rest. It's 1 point. This 1 is not stored on the computer. We don't need to store it because it's always 1. But these are the digits after the decimal point. No, not after the decimal point, but the digits after the dual point. So let's talk about the number 1.1001. Being a dual number, that is 1, this one, plus, what is that? If it was a decimal number, it was 1 times a tenth. But it's a dual number, so it's 1 times a half. So it's a half. Plus 0 times a quarter, plus 0 times 1/8, plus 1 times 1/16. And so in total, we have this number. Minus 1 times 2 to the power of 2. So it's 4 times this number. And this is 4 plus 2 plus a quarter. And so it's 6.25, but minus 6.25. Let's check that. We can check it with the help of MATLAB or with the help of Octave. Let's say A is minus 6.25. So we have this number. And now we can say format hex and let's display A again. And we get this C019 and a lot of zeros following. Let's check that on our paper. The number we have seen on the screen was C019 and 12 zeros following. What does that mean? For the purpose of being better readable, we prefer a different type of displaying these lots of zeros and ones. We take 4 bits and we will make a hexadecimal number out of these 4 bits. So let's prepare something. So with the help of this list, we can interpret this number. C is 1100. 0 is, of course, 1 is, and 9 is. And now a lot of zeros. And now let's compare that. 1 1 0 0 0 0 0 1 1 0 0 1 and zeros following. So the number minus 6.25 is stored internally in this form, 64 bits, and these are the bits. So now we know how to interpret a 64-bit sequence as a floating point number. And now I will give you a second example, and you can try to interpret this number. So please feel free to do the job we have done here. Please stop the video, do the job, and then continue watching. Now again, we have 3 parts. These 3 parts are always the same 3 parts. The first bit, the following 11 bit, and the following 52 bits. And what is that number? It's this time minus 1 to the 0, so it's a positive number. The first bit is the sign bit. If it's 0, it's positive. If it's 1, it's negative. Okay, times 2 to the power of, what happens here compared to here? This number is 1 more than this number. It's 1024 plus 2, what is 1026. This is always here 1023, and now it's 1.5 zeros and then a 1, 4 zeros and a 1, and so on. So we have plus 2 to the power of, no, it's not 1024, it's 1026. 1024 plus 2 is 1026. So it's 2 to the power of 3, what is 8, times 1 plus a half, a quarter, 1 over 8, 1 over 16, 1 over 32, 1 over 64. 128, 256, 512, 1024, 2048, plus not so much. Okay, and now we can calculate that with an electronic calculator, and then you will get 8.1289 something. But if you really do the job for all the bits, not only till here, but also using all these bits, it is 8.13, but not completely 8.13. It's the rounded version of 8.13. The point is that here, if these are the numbers, then 8.13 is here, and there are 2 numbers next to it, and we only can store these numbers. 8.13 cannot be stored without a rounding effect. So internally, if we want to store 8.13, we are looking for the next available number, and we store that number, and then we get that. Let's check that using Octave or using MATLAB. Let's say B is 8.13 and we see it's 4020428 and so on. Please write down this number on a paper, and now I will go back to the paper. What is that number? It's a 4. What is that? It's a 0. What is that? It's a 2. What is that? It's a 0. What is that? It's a 4. You can do that with that table. It's a 2. It's a 8. It's a F. It's a 6. It's a 12. 12 is C. It's a 2. It's a 8. It's a F again. It's a 5. It's a 12. What is C? And it's a 3. And that is the number we have seen on the screen, 4020428F. 6. No, I checked that. It was not a 6. So which was that? This is not a 6. It's a 5. It was 5C28 F5C3. Yes, this was the number we have seen on the screen. And now let's have a look in my script. Floating point numbers. Here it is written what we have talked about. And here is another example. This time we are talking about the number 3.203125. And in MATLAB we can check all that. And then we can talk about the number 6 in MATLAB. Take that as a third example. So these were the basics of floating point numbers. Our first chapter, our first video about floating point numbers. Some more videos are following, doing also the vice versa. What if we want to store the number 8.13? What goes on internally? And that is the topic of our next video.